Contingency tables are a great way to organize different sets that belong to the same sample. For example, we're looking at a sample of 100 individuals, and they're separated by different types of characteristics. For example, of these 100 individuals, we know that they have identified as either males or females, as well as being right-handed or left-handed. This table helps us see how many people are identifying as each type of group, whether it be a gender group or a handed group. One thing that's really useful to do in tables like this is to find totals of each type of category. For example, in my right-handed column, I can see that 43 of those who identify as male are right-handed, and 44 of those who identify as female are right-handed. So I could find my total of those who are right-handed just by adding down the right-hand column. So it would be 87. We have 87 right-handed individuals inside of our sample. We can do the same thing for left-handed people. 9 plus 4 would give us the total of those who are left-handed. So we have 13 left-handed individuals. And we can double check that we've accounted for everyone by adding the right hands plus the left hands to see our total does match the 100 from our sample. We can do the same thing with the other two categories. For those identifying as male, we have 43 and 9. Combining those together, we would have 52. And those identifying as female, we have 44 combined with 4, so that would be 48. And again, if I added together the males and the females in this study, I should get 100 of those who are part of the study. So we can see all of our totals. If I want to know total males, I just read through the male column, there's 52. Females, read through the female column, there's 48. How many people are left-handed? We have 13. How many people are right-handed? We have 87. So that's going to be a quick way to help us keep count of different groups. Now we're ready to start calculating probabilities. We know that probabilities are fractions, ratios, percents, where the possible outcomes goes on the denominator, and the ways of getting the event you're interested in goes in the numerator. We're going to let M represent males, F represent females, R right-handedness, and L left-handedness. So probability that the subject that we randomly select in the study identifies as male would be the 52 males that there are to randomly select out of the 100 people in the study. Probability that the person we randomly select identifies as female would be 48 out of 100. There are 48 females in this study. Probability that the person we randomly select is right-handed would be 87 out of 100. And the probability that the person we select is left-handed would be 13 out of 100. Notice that in every one of these probabilities we just found, the denominator is the same. The only thing that's changing is the number on top, and that number always represents the total possible ways that the event we're considering could happen. Now we're ready to look at some of the AND events. So male and right-handed means we're looking for someone who's in both the male row and the right-hand column. So we're considering all of these members of the study. These are all the males. And all of those who are right-handed. And is saying that I want one person that has both characteristics. The 44 here represents those who identify as female. We're looking for someone who's both male and right-handed. The 9 here represents males, but they're left-handed. So the only people in the study who identify as both male and right-handed are these 43 individuals. That would be our numerator. Denominator is still 100. We're still looking at 100 participants in the survey. Let's take a look at female and left-handed. That would be anybody who's in both the female row and the left-hand column. Now again, we're not talking about the 9 individuals who are left-handed but are male. We're not talking about the 44 females who are right-handed. We're only talking about the 4 females who are also left-handed. The probability of randomly selecting someone in the study who is both female and left-handed is 4 out of 100. Whenever we talk about 2 events combined with an and, we're looking for where they overlap. If we're talking about 2 events and we combine them with an or, then we're actually going to count all of the numbers that belong in either of the 2 categories. So let's look at the probability that we randomly select someone who identifies as male or female. That would be all of those in the male row, as well as all of those in the female. Notice there's no overlap here. In this study, all 100 participants picked that they identify as either male or female. There's no overlap here. So we would count all 4 of the numbers in the table, and we happen to know that that's all of the 100 participants in the study. What if we wanted male or right-handed? We've already highlighted this row and this column combo before, but this time, instead of crossing out the numbers that are not overlapping, we're going to include them. We have 44 individuals who are right-handed but female, 43 individuals who are male and right-handed, and 9 individuals who are male but left-handed. We're not saying that you have to have both criteria when we say male or right-handed. We're saying as long as you have one, we're satisfied. So we would add up the 44, the 43, and the 9 to make our numerator. The denominator would still be 100. That would be 96 out of 100. What about if we looked at female or left-handed? So again, we've already highlighted this row and column combination, but this time we're not looking at the overlap, we're looking at combining anyone who belongs to either the female group or the left-handed group. So we're adding the 9, the 4, and the 44. All over 100. That would be 57 over 100. Next, let's take a look at a complement. The complement of the M event, or the male complement group, is anybody who's not in the male row. So we could essentially just ignore anything that's in the male category, and that will show us how many possible outcomes there are for the complement. We know that the only people left in the study who are not in the male group are the females. Whether they're left or right-handed doesn't matter. So we're looking at both of these numbers here, the 44 and the 4, which is 48. So the probability of male complement would be 48 over 100. Now let's take a look at some conditional probabilities. The probability that somebody randomly selected is right-handed, given we know that the person that we have randomly selected is a male. Whenever we look at conditional probabilities, you're always assuming that the second event that's written in this notation definitely had to have happened. So if I know that I'm only looking at males, I can ignore all of the females. And then I can say of the males, of the 52 males in the study, how many of them are right-handed? This is shrinking our sample space. Instead of talking about all 100 participants, we're only talking about the 52 males in the study. And of those 52 men, how many are right-handed? 43. So the probability that the individual we select is right-handed, given they are male, is 43 out of 52. If we look at the probability that we select a female given that they're left-handed, we're shrinking our sample space to only consider the left-handed individuals. So we will ignore anybody who's right-handed. Now our sample size has shrank again. It's no longer 100. Our sample size is now 13. So our denominator is only talking about the 13 left-handed individuals in the study. And now we want to know, of those 13, how many of them are identifying as female? There are 4. So the probability that we randomly select a female, given we know that the individual is left-handed, is 4 out of 13. And just to drive the idea home that conditional probability is not commutative, what if we reversed the order of those two events? What's the probability that we randomly select someone who's left-handed, knowing that they're definitely identifying as female? Well, this time we're shrinking our sample space to talk only about the females in the study, nobody else. Our sample size is now 48. We need to count, of those 48 females, how many of them are left-handed? There are 4. So the probability that we randomly select a left-handed person, given we know that they are a female, is 4 out of 48.